right now, at this exact moment, something is dying in the dark. 14 billion miles from where you are sitting. It has no heartbeat, no breath, no blood moving through any kind of vessel. But it is alive in the only way a machine can be alive. It is still transmitting, still sending back a whisper of a signal across the most violent emptiness that has ever existed. A signal so faint that the entire energy carried by it, received here on Earth, is less than a single quadrillionth of a watt, less than the energy of a single falling snowflake, less than anything you have ever measured with your bare hands. And that whisper is fading. Voyager 1 is the farthest human-made object ever launched into the cosmos. It has traveled through the heliopause, the boundary where the sun's solar wind finally collapses and surrenders to the interstellar medium. And it has crossed into the true void. Not the emptiness between planets, not the quiet between moons. The actual interstellar ocean, the space between star systems, the place where no particle from our sun has ever touched the dust around it. That place. Voyager 1 is there right now, moving, drifting at roughly 38,000 miles per hour in a direction we have named, almost poetically, toward the constellation Ophiuchus. It will never stop, but it is dying. The spacecraft was launched on September the 5th, 1977. That means it has been alive, transmitting, processing, adjusting, surviving, for longer than most humans reading this have been on Earth. It survived the radiation belts of Jupiter. It captured the first close images of Saturn's rings in photographic detail that shattered what astronomers thought they understood. It watched Titan's thick orange atmosphere from a distance no probe had ever achieved. It crossed the termination shock, the zone where solar wind slows dramatically as it meets the pressure of interstellar space. And then it crossed the heliopause itself, a boundary so far from home that the light from the sun, traveling at 186,000 miles per second, takes over 22 hours to reach it. 22 hours of light travel time, just to reach where Voyager is now. And the engineers who built it, the men and women at NASA's Jet Propulsion Laboratory, who wired its circuits by hand, who soldered its instruments with careful fingers in a clean room that smelled of metal and ambition. They gave it a power source. 3 radioisotope thermoelectric generators, RTGs, plutonium-238 cores producing heat through radioactive decay, converting that heat into electricity through a process of thermoelectric conversion so elegant it requires no moving parts, no combustion, no fuel tank to run dry. Just the slow, patient, inevitable decay of atoms. Each plutonium nucleus breaking apart at its own pace, shedding heat across decades like an ember that refuses to go cold. But even embers die. Plutonium-238 has a half-life of 87.7 years. That means every 87. 7 years, half of what remains loses its ability to produce heat. The power output of Voyager's RTGs has been declining since the moment of launch, slowly, relentlessly, mathematically, at a rate of roughly 4 watts per year. 4 watts? The kind of power that barely keeps a dim nightlight burning in a child's bedroom. That is what Voyager loses every year, out there in the dark between the stars. It began with roughly 470 watts. It now produces somewhere around 2% of that. The engineers have been performing a kind of triage for years, shutting down heaters to preserve power for the instruments, allowing parts of the spacecraft to drop to temperatures that, on Earth, would shatter metal, turning off redundant systems, making impossible choices between which piece of the spacecraft lives and which piece goes cold and silent forever. And still, Still, the power keeps dropping. The margin keeps shrinking. The numbers keep closing in like walls. There is no repair mission coming. There is no emergency procedure that can reach it. At 38,000 miles per hour, even if humanity launched the fastest spacecraft ever conceived today, this second, right now, it would take decades to even approach Voyager's current position. And by that time, Voyager would already be a silent, frozen monument drifting through interstellar space. Unreachable, untouchable, the most remote artifact of human civilization, spinning slowly through a darkness so complete it has no name in any human language. The death of Voyager 1 is not a metaphor. It is physics, and it is coming whether we are ready for it or not. To understand what is being lost, you have to understand what was built. Voyager 1 weighs 722 kilograms, less than a mid-size automobile. Its main antenna, the high-gain dish that points back toward Earth with a precision that defies imagination, measures 3.7 meters across. The entire spacecraft, fully extended with its booms and instruments, spans roughly the width of a tennis court. And yet this object, this small, almost fragile collection of metal and circuit and wire, has outlasted every expectation, every projection, every model that the engineers who built it dared to write down on paper. They designed it for a 5-year primary mission. It is now approaching its 49th year of continuous operation. 49 years in interstellar space, alone. The computer at its core, the flight data system, the attitude control computer, the command subsystem, runs on technology so ancient by modern standards that a single chip inside your wireless earbuds contains more raw processing power. Voyager's computers operate in the kilobyte range. Not megabytes, not gigabytes, kilobytes, the kind of memory that cannot hold a single photograph taken by a modern smartphone. And yet, these processors have been navigating the spacecraft through gravitational fields, coordinating instrument readings, managing power loads, and encoding scientific data across a distance so vast that a radio signal, moving at the speed of light, takes more than 22 hours to make the one-way trip between Voyager and the nearest receiving dish on Earth. 22 hours to send a command, 22 hours more to receive a reply. Any conversation with Voyager 1 takes 2 days just to complete a single exchange. Think about what that means, philosophically, not just technically. Every instruction sent to this spacecraft is an act of extraordinary faith. Engineers at JPL type a command, transmit it, and then wait. They go home, they sleep, they wake up, they eat breakfast, they drive back to work. And only then, the next morning, does the confirmation arrive that Voyager received what was sent and responded accordingly. It is communication across a gulf so immense that it stops feeling like engineering and starts feeling like something else entirely. Something closer to prayer. You speak into the void and you wait. And you hope that something on the other side is still listening. The power that sustains that listening is the heart of the crisis. The 3 RTGs, the radioisotope thermoelectric generators mounted on a boom extending from Voyager's body, work through a principle of breathtaking simplicity. Plutonium-238 decays spontaneously. Its nucleus is unstable, and that instability releases heat. That heat flows through a set of thermocouples, junctions of 2 dissimilar metals. And the temperature difference between the hot side facing the plutonium and the cold side exposed to the near absolute zero of space generates a voltage. that voltage becomes electricity. No turbines, no combustion chambers, no moving parts of any kind. Just the fundamental restlessness of an atom converted patiently into current year after year, decade after decade, in the silence between the stars. It is one of the most elegant power systems ever conceived. And it is running out of elegance. The plutonium cores that once glowed with enough heat to produce 470 watts at launch now yield somewhere around 20 watts of usable electrical power. 20 watts. The thermal output is still there. Plutonium does not stop decaying on command. But the thermocoupled junctions themselves have degraded over decades of operation. The temperature differential that drives the voltage has narrowed as the junction materials age and their thermoelectric efficiency erodes. This is not a problem that can be fixed remotely. The degradation is physical, structural, atomic. It is written into the material itself the way age is written into bone. You cannot send new thermocouples across 14 billion miles. So the engineers do the only thing left to do. They choose. Every few years, sometimes more frequently now, the team at JPL evaluates which instruments and heaters can be switched off permanently to preserve power for the systems that matter most. The ones that still return scientific data. The ones that still justify the 22-hour conversation. In 2019, a heater for the cosmic ray subsystem was turned off, allowing that instrument to drop to temperatures approaching -79 degrees Celsius, far colder than it was ever rated to operate. And yet, it kept working. The instrument kept returning data. It held on in conditions that should have killed it, like a climber clinging to an icy face long after the warmth has left their fingers. That resilience is not accidental. It is the product of engineering margins built in during construction, tolerances wider than the mission profile demanded, components tested to failure and then tested again, redundancies layered into systems that were expected to last 5 years and ended up lasting 50. The people who built Voyager built it as if they suspected, somewhere deep in the quieter part of their minds, that it might go on longer than any of them would live to see. Some of them were right. Many of them did not live to see this moment. And here is the philosophical weight of that fact. The part that science communicates in numbers, but the human mind receives as something heavier than numbers. The engineers who soldered Voyager's circuits are aging or gone. The specific institutional knowledge of how this particular spacecraft behaves, its quirks, its anomalies, its decades of accumulated eccentricities, exists now in a shrinking group of people. Some of them retired, some of them recalled from retirement specifically because no one else carries what they carry in their memory. When Voyager eventually goes silent, it will not just be a spacecraft that dies. It will be the last living connection to a generation of engineers who believed, in the early years of the space age, that the universe was something humanity could reach out and touch. They were not wrong about that. But touch is different from hold. Voyager proved that the cosmos can be touched, can be grazed, briefly, by human ingenuity and human will. What it is now teaching us, in these final years of transmission, is that we cannot hold on, that everything we send into the dark eventually loses its warmth, that the universe does not accommodate our desire to keep things alive indefinitely. It accommodates only physics, and physics, in the end, is indifferent to everything we have ever felt about the things we have made and sent away and loved from a distance of 14 billion miles. The cold does not hate Voyager. That is almost the hardest part to accept. It simply does not care. And in that indifference lives a truth about the cosmos that no telescope has ever captured, and no equation has ever fully expressed. The universe is not cruel. It is not kind. It is vast and cold, and governed by laws that were never written for us. Voyager is learning that lesson for all of us, 1 watt at a time. There is a place where the sun ends, not where its light ends. Sunlight, technically, travels forever, growing dimmer across billions of light years until it becomes indistinguishable from the background radiation of the universe itself. What ends at a specific and measurable boundary is the sun's wind, the constant outflow of charged particles, electrons, protons, alpha particles, that the sun breathes outward in every direction at speeds between 250 and 750 kilometers per second. This solar wind inflates a vast, invisible bubble around our entire solar system, a region called the heliosphere. And for billions of years, it has held something back: the interstellar medium, the ancient, cold, dense river of matter that flows between the stars. Voyager 1 crossed the outer wall of that bubble on August 25, 2012. It was the first human-made object in history to leave the sun's domain entirely. The crossing did not look dramatic from the outside. There was no flash of light, no shockwave visible in any telescope, no sound. Sound being a concept that loses all meaning in a medium too sparse to carry a pressure wave. What happened was quieter and stranger than any explosion. The plasma density around the spacecraft suddenly increased. The magnetic field orientation shifted. The flux of low-energy particles from the sun dropped sharply, and the intensity of galactic cosmic rays, high-energy particles accelerated by supernova and other violent events scattered across the Milky Way, rose sharply and unmistakably. In the data streaming back across those 22 hours of void, the signature was unambiguous. Voyager had crossed a threshold that humanity had theorized about for decades and never once touched. It touched it at 38,000 miles per hour with no fanfare on a Tuesday. The most significant boundary crossing in the history of exploration happened on an ordinary workday. What lies beyond that boundary, what Voyager now moves through every second of every day, is the interstellar medium. And the interstellar medium is not nothing. That is perhaps the most important correction science has made to the popular imagination's picture of space. Space is not empty. It never was. The interstellar medium is a diffuse but real substance, a thin soup of gas, dust, plasma, and magnetic fields that permeates the entire galaxy. On average, it contains about 1 atom per cubic centimeter. 1 atom. In a volume the size of a sugar cube, you might find a single hydrogen nucleus, drifting in a darkness so cold, around 10 degrees above absolute zero in the coldest regions, that it approaches the theoretical floor of all thermal motion. And yet, it is structured. It has texture. It has regions of different temperature, density, and ionization that Voyager's instruments can detect and distinguish. The plasma wave science instrument aboard the spacecraft has been measuring the density of electrons in the interstellar medium, and what it has found challenges simple models. The medium is not uniform. It is layered, turbulent in ways that are slow and vast, marked by the echoes of ancient stellar explosions whose shock waves have been traveling outward for thousands of years and are still moving, still shaping the medium Voyager now crosses, long after the stars that produced them have collapsed and gone cold. Voyager is sailing through the afterglow of dead stars. Every measurement it returns is a reading taken inside a graveyard that is also a nursery, because the interstellar medium is not just the residue of what has died. It is the raw material of what will be born. The hydrogen and helium and trace quantities of heavier elements drifting through the space Voyager occupies right now will, in some distant future measured in millions of years, condense under gravity into clouds. And those clouds will collapse into protostars. And those protostars will ignite, and around some of them, perhaps most of them, planets will form. And on some of those planets, given enough time and chemistry and the particular kind of luck that produces self-replicating molecules in warm, shallow water, something might arise that eventually points a dish at the sky and wonders whether it is alone. The atoms Voyager is moving through right now have always been here. Long before the sun was born, long before the Earth accreted from the disk of debris that surrounded our infant star. These atoms were part of earlier solar systems, earlier planets, earlier oceans, or the spaces between them. They carry no memory in any conscious sense, but they carry information. Their isotopic ratios, their ionization states, the specific energies at which they emit and absorb light. All of these encode the history of their origin. And Voyager, in its final years, is reading that history for the first time, translating the biography of the galaxy written in particles too small to see, too ancient to fully comprehend. No instrument on Earth can do what Voyager is doing right now. None. Not one. Telescopes observe the interstellar medium from the inside of the heliosphere, through layers of solar wind that distort and contaminate the signal. Every measurement made from Earth, or from Earth orbit, or from anywhere within the sun's bubble, is filtered through a medium that the sun itself has charged and heated and shaped. Voyager, beyond that bubble, takes its readings in the raw, unfiltered, direct. It is the difference between studying the ocean from the shore and putting your hand into the water. For decades, we studied the shore. Voyager put its hand in, and it is still reading, still measuring, still sending those readings home across 22 hours of light-speed silence. The cosmic ray subsystem counts high-energy particles, the shrapnel of stellar violence from across the galaxy, and finds them arriving from all directions with an isotropy that confirms Voyager is genuinely outside the sun's protective sheath. The magnetometer traces the interstellar magnetic field, a structure so large and so ancient that it predates our solar system by billions of years. The plasma wave instrument listens to the electromagnetic oscillations of the medium itself, oscillations that have been compared, in their mathematical structure, to the lowest notes of an instrument so enormous the human mind cannot hold its scale. The universe is playing a frequency Voyager is just barely old enough, just barely far enough to hear. And soon, it will not be able to hear anything at all. This is the weight that the word dying carries when applied to Voyager 1. It is not merely the loss of a machine. It is the closing of an ear. The only ear humanity has ever placed beyond its own solar doorstep, beyond the last wall of the sun's influence in the true interstellar dark, is going deaf, 1 watt at a time, in a place so remote that when it finally falls silent, we will not hear the silence arrive. We will simply stop receiving the signal, and we will know, from its absence, that the most extraordinary listener we ever built has at last gone quiet in the oldest ocean in the galaxy. We named that ocean nothing. We had no name ready. We had not believed, until Voyager, that we would ever be able to touch it. In November of 2023, Voyager 1 lost its mind. Not catastrophically, not silently, in a way that was almost more unsettling than either of those. It kept talking, kept transmitting its carrier signal back across the 22-hour gulf. But what it said made no sense. The Flight Data System computer, one of 3 onboard processors responsible for packaging scientific and engineering data before transmission, began sending back a single repeated pattern of ones and zeros that corresponded to no valid data format in any of the codebooks JPL engineers used to decode incoming signals. It was as if someone had asked a question and received, in return, a perfectly articulated sentence in a language that had never existed. Voyager was speaking, but no one could understand what it was saying. The team spent months, diagnosing the problem across a communication delay that made every hypothesis a days-long experiment. Send a command. Wait 22 hours. Receive a response. Analyze it. Form a new hypothesis. Send another command. Wait again. The process of troubleshooting a computer glitch that would take a technician 45 minutes to resolve in a laboratory on Earth consumed the better part of half a year when the laboratory is 14 billion miles away and every diagnostic query travels at the speed of light. What they eventually found was this: a single chip, one chip, roughly 3% of the memory in the affected computer, had corrupted. The code stored in that small region of memory was no longer intact, and because that particular region happened to contain the instructions the computer used to package data for transmission, the corruption cascaded through every subsequent output, rendering it unreadable. The spacecraft itself was functioning. Its instruments were operational. Its gyroscopes were holding attitude. Its antenna was pointed at Earth with the same extraordinary precision it had maintained for decades. But its ability to tell us any of that, to translate its own condition into a format we could read, was broken. Voyager knew it was alive. It simply could no longer explain itself to us. The solution the engineers devised was staggering in its delicacy. Because the corrupted memory region was too damaged to repair directly, they could not simply rewrite the affected code in place. Doing so risked compounding the corruption unpredictably. Instead, they redistributed the code. They broke the affected instructions into fragments and stored those fragments in different, healthy sections of the computer's memory. Then rewrote the references so that the processor would call each fragment in the correct sequence, assembling the function from pieces scattered across the machine like a sentence whose words have been shuffled into different drawers, but whose meaning can still be recovered if you know which drawer to open first. They tested this solution on a software model of Voyager's 1977-era computer systems maintained on the ground. Then they composed the patch, carefully, surgically, the way a restorer applies pigment to a crumbling fresco, and transmitted it. And then they waited. 45 hours round trip for the patch to travel out and the confirmation to travel back. 45 hours in which no one at JPL could know whether the most distant spacecraft in human history had received the repair, accepted it, executed it correctly, and survived. On April 20th, 2024, coherent data returned from Voyager 1 for the first time in 5 months. The engineers wept, some of them openly at their desks in a building in Pasadena, California, while 14 billion miles away, a 722-kilogram machine with a 1970s processor and a dying power source quietly resumed its work, measuring cosmic rays and plasma density in the interstellar dark as if nothing had happened. As if it had simply been thinking and had now decided to share its thoughts again. That moment, the return of coherent signal, deserves to be held in the mind. No mind for longer than news cycles allowed it to breathe. Because what it represents is not merely a technical victory. It represents something about the nature of care itself. The team that saved Voyager did not do it for commercial return. There is no revenue generated by a spacecraft beyond the heliopause. There are no passengers to protect, no cargo to deliver, no contractual penalty for failure. They did it because Voyager is worth saving. Because the data it returns is irreplaceable. Because the object itself has become something that exceeds its original function. It has become a kind of witness. And the people who talk to it every day understand, in the way that only sustained attention can teach, that witnesses must be kept alive as long as possible. To care for something you know, you will lose anyway. That is not futility. That is the most human thing there is. The team that operates Voyager today is a deliberate mixture of veterans and younger engineers brought in specifically to absorb institutional knowledge before it disappears with the generation that created it. There are people working on Voyager right now who were not yet born when it launched. They are learning to speak the spacecraft's language. Its particular communication protocols, its decades of behavioral quirks, the subtle signatures in its telemetry that indicate nominal operation versus early-stage anomaly. From people who have spent their entire professional lives in conversation with it. It is an apprenticeship unlike any other in the history of technology, a masterclass in how to maintain a relationship with something that is irreplaceable and unreachable and slowly, inevitably, dying. And the relationship is genuinely bidirectional, in a way that matters. Voyager sends data. The team receives it, interprets it, acts on it, and sends responses. The spacecraft's behavior changes based on the commands it receives. The commands change based on what the data reveals. This feedback loop, slow, stretched across light hours, mediated by ancient hardware and modern interpretation, is nonetheless a loop. It closes. Something on one end responds to something on the other. By the loosest and most careful definition, it is a conversation. Perhaps the longest distance conversation ever conducted between human beings and anything they have made with their hands. What makes it heartbreaking is knowing its end is structural, not accidental. The 2023 anomaly could have been the end. A different chip failure in a different memory region might have produced a corruption that no patch could address. A cascading failure that silenced the spacecraft permanently before its power budget forced the issue. That it was recoverable was not guaranteed. It was the product of luck as much as skill. And luck is not a resource that replenishes itself on demand. Every anomaly that Voyager survives from this point forward will be survived against narrower margins, with less power to spare for recovery operations, with instruments already operating below their rated thermal tolerances, with a team working against a clock that has no pause function. They are not trying to prevent the end. They know they cannot. They are trying to honor what remains. That distinction between prevention and honoring is one the engineers themselves have articulated in interviews and in the quiet language of their choices. Every heater they leave on a little longer than the power budget strictly allows. Every instrument they keep active past the point of conservative management. Every hour of deep space network antenna time devoted to listening for Voyager's signal rather than some other mission. These are not the choices of people who believe they will win. They are the choices of people who understand that some things deserve your full attention, even, especially, when you already know how the story ends. Voyager 1 is being accompanied to the threshold by the people who built it, by the people who learned from those people, by all of us, in whatever small way our awareness constitutes accompaniment. That is what the dark looks like. From the human side, bolted to the side of Voyager 1, there is a 12-inch disc made of gold-plated copper. It weighs next to nothing. It adds no thrust, no power, no scientific capability to the mission. It serves no engineering function whatsoever. It is there for an entirely different reason. One that has nothing to do with physics and everything to do with the particular kind of longing that defines the human species. The longing to be known, to reach across distances that dwarf comprehension and say to whatever might be listening, "We were here. We existed." This is what we sounded like. The golden record contains 115 images encoded in analog form, greetings in 55 human languages, 90 minutes of music drawn from cultures spanning every inhabited continent, and a selection of natural sounds. Wind moving through trees, rain falling on open water, the low resonant surge of ocean waves, the calls of birds and whales, the cry of a newborn child, the quiet, intimate sound of a human kiss. It contains a spoken message from the Secretary General of the United Nations and a message from the President of the United States, both now dead. It contains a message from a child. It contains, encoded in the geometry of its cover, instructions for how to build a device capable of playing it, instructions written not in any human language, but in the universal grammar of hydrogen, the most abundant element in the universe, used as a physical constant from which all other measurements on the cover can be derived. It was designed to be read by someone who has never met a human being. The people who assembled the record, led by the astronomer Carl Sagan, who understood better than almost anyone of his generation that science and meaning are not enemies but companions, worked under a deadline of weeks. They had almost no time and almost no precedent. No one had ever tried to compose a portrait of an entire civilization before. No one had ever asked what you would include if you could only include everything that mattered. And you had to fit it on a 12-inch disc, and your audience might not have ears. They made their choices with the urgency and the fallibility and the profound sincerity of people who knew they were doing something that would outlast them by an unimaginable margin. They were right about that. By a margin that has no name in any human language. In approximately 40,000 years, Voyager 1 will make its closest approach to another star system. The star is called AC +793888, a dim red dwarf in the constellation Camelopardalis, and Voyager will pass within 1.6 light years of it. Still an enormous distance by human standards, but a near miss by the scale of interstellar space, where the average distance between stars in our region of the galaxy is 4 to 5 light years. At that point, no human civilization will exist in any form recognizable to us today. The languages on the golden record, all 55 of them, will be as alien to whatever minds inhabit Earth in 40,000 years as the cave paintings of Lascaux are to a software engineer in 2024. The political entities whose leaders recorded messages for the disk will have been gone for tens of thousands of years. The specific anxieties, the specific joys, the specific textures of daily life that the record's curators tried to capture. All of it will be archaeological. And Voyager will still be moving, still carrying the record, still intact, because space, in its vast indifference, is also a perfect preservative. There's no oxygen to oxidize the gold plating, no moisture to degrade the copper substrate, no ultraviolet radiation beyond the heliosphere intense enough to cause significant surface damage over human timescales. No microbes, no entropy of the biological kind, no weather of any description. The same absence that makes space lethal to living things makes it extraordinarily gentle to dead ones. Voyager, once its transmitters fall silent and its instruments go cold, will become something that the universe treats with more care than it has ever treated anything alive. Not out of reverence, but simply because nothing out there will disturb it. It will drift for billions of years in a condition closer to perfect preservation than anything on Earth has ever achieved. In 5 billion years, when the sun exhausts its hydrogen fuel and expands into a red giant, swelling to a radius that will engulf Mercury, then Venus, then, in all probability, Earth itself, boiling the oceans, stripping the atmosphere, reducing every city and forest and ocean trench and fossil and book and painting and grave to plasma. Voyager 1 will be somewhere between 1 and 2 light years from the sun, far enough that even the dying star's vastly expanded envelope will not reach it, far enough that the catastrophe that ends our world will be, from Voyager's position, merely a distant brightening. A star that gets briefly, dramatically larger, then collapses into a white dwarf and begins its own slow cooling across billions of additional years. Voyager will not witness this. It will have no instruments left to measure it. But it will survive it. The golden record will outlive the Earth. That sentence should stop you completely. The disc bolted to the side of a 722-kilogram machine launched from Cape Canaveral in 1977, assembled in weeks by a team of human beings who were worried about the deadline, will continue to exist in some form after the planet that produced it no longer does. The sounds of rain and ocean and whale song and a child's first cry, encoded in the grooves of gold-plated copper, will travel through the interstellar medium long after every ocean has been vaporized, long after every child and every whale and every rain-soaked forest has been reduced to the same undifferentiated plasma that the sun will make of everything it once warmed. This is not a comforting thought. It was not meant to be. It is a clarifying one. The golden record forces a confrontation with scale, with the vertiginous, destabilizing reality of deep time that almost nothing else in human experience can produce. We are accustomed to thinking of our artifacts as things that outlast us by centuries, perhaps millennia. Pyramids, cathedrals, the Dead Sea Scrolls. But Voyager's trajectory and the physics of stellar evolution combine to produce something categorically different. An artifact that outlasts not just its makers, not just their civilization, not just their species, but the very planet on which all of those things arose. And yet it began with such ordinary human things. A deadline, a committee, an argument about which piece of music best represented the breadth of human feeling. Someone decided to include Bach. Someone fought for Chuck Berry. Someone wept, probably, over what had to be left out. The most durable object humanity has ever made was assembled by people who were worried about what to include. That is the specific texture of the human condition that the golden record preserves without meaning to. Not our greatest monuments, not our most refined philosophy, not our most elegant mathematics, though it contains all of those. But the irreducible fact that we are creatures who, when confronted with the infinite, respond by making choices, by including this and not that, by saying, of everything we are, this is what we most want you to know. We wanted to be known, and we sent that wanting into a darkness so deep that knowing whether it was ever received is something no version of humanity that has ever existed or ever will exist will live long enough to learn. The message travels on. The silence of its destination is not a failure. It is simply the scale of the ambition made honest. There will come a day, no one can say exactly when the signal stops, not dramatically. There will be no explosion, no final burst of data, no farewell encoded in the last transmission. The power will simply drop below the threshold required to drive the transmitter, and the carrier wave that has been crossing the solar system and the interstellar medium for nearly 5 decades will vanish. One moment it will be there. That whisper of a signal, thinner than any thread, crossing 14 billion miles to arrive at the great white dishes of the deep space network, with less energy than a snowflake landing on still water. And then it will not be there. And the silence that follows will be indistinguishable to any instrument from the silence that preceded the launch. The universe will not mark the moment. No star will flicker. No frequency will shift in memoriam. The most traveled object in human history will go quiet, and the cosmos will not notice. We will notice. That is the only difference. And that difference between a universe that does not register the loss and a species that cannot stop registering it is the entire territory of what it means to be human in a cosmos that was not made for human meaning. Carl Sagan, who loved Voyager the way a parent loves something they had a hand in making and cannot protect forever, once asked the spacecraft's cameras to turn back towards home. It was February 14th, 1990. Voyager 1 was 6 billion kilometers from the sun, already farther than any camera had ever pointed from. And in the resulting photograph, a mosaic of 60 frames taken through colored filters, Earth appears as a point of light so small it barely registers against the scattered rays of the sun contaminating the image. A pale blue dot, a mote of dust suspended in a sunbeam. Sagan described it as the loneliest and most clarifying image ever taken, because it does not show us how magnificent we are. It shows us how small, and in that smallness, paradoxically, it shows us how extraordinary. Because something on that dot looked outward, built an instrument, sent it into the dark, and then had the courage to turn the camera around and look back. We are the only thing in the known universe that has ever photographed its own home from interstellar distance and understood what it was looking at. That image will not age. Its meaning compounds with time, because as the decades pass and Voyager moves deeper into the interstellar medium, the pale blue dot in that photograph recedes not just spatially, but temporally. It becomes a record of what the Earth looked like at a specific moment, from a specific distance, before everything that has happened since. There are people alive today whose entire lives have elapsed since that photograph was taken. There are generations who have grown up knowing themselves as inhabitants of the pale blue dot, shaped by what it means to see your world from outside it. Voyager gave us that. Voyager gave us the only external perspective on our home that any member of our species has ever had access to. And when Voyager goes silent, we lose the only object that is simultaneously moving away from us and pointing, in some essential sense, back. Every other telescope looks outward. Voyager was the one that, for a moment, looked home. There is a grief in this that conventional language handles poorly. We do not have a well-developed vocabulary for mourning machines. We have rich traditions for mourning people, for mourning places, for mourning the ends of eras. But the loss of Voyager 1 does not fit cleanly into any of those categories. It is not the death of a person. It is not even precisely the end of an era, because eras end in events, battles, discoveries, transitions of power. And Voyager's silence will be an absence rather than an event. A signal that ceases, a conversation that simply stops mid-sentence because the speaker ran out of the only fuel available. And the laws of thermodynamics, which have never once suspended themselves for anything, will not suspend themselves for this. And yet the grief is real. It is the grief of finitude confronting infinitude. The grief of having sent something irretrievable into a place where retrieval was never the point. The grief of caring about an outcome you cannot influence, for an object that cannot reciprocate your caring across a distance that makes the word distance itself feel inadequate. We grieve Voyager because grieving it is a way of acknowledging what it cost us to make it, what it cost us to let it go. Because we did let it go. That is the part the physics does not fully convey and the philosophy cannot fully absorb. At every stage of Voyager's journey, the people responsible for it had the option to shut it down, to stop listening, to redirect the Deep Space Network antenna time to younger missions, to declare the mission complete and close the books. They chose repeatedly and deliberately not to. They chose to keep listening, to keep maintaining the conversation, to keep caring for something that was moving away from them at 38,000 miles per hour and would never, under any physical scenario consistent with the known laws of nature, return. That choice, to maintain devotion in the full knowledge of permanent separation, is not unique to Voyager. It is the structure of every love that outlasts the possibility of reunion. Every prayer directed at something that cannot respond. Every letter written to the dead. Every moment a human being has chosen to honor a connection that the physical universe has already severed. Voyager did not teach us this about ourselves. It revealed what was already there, projected onto a scale large enough to see clearly from the outside. We are the species that grieves across 14 billion miles. That is not nothing. That is almost everything. When the signal finally stops, and it will stop within the next few years, as the power budget collapses below the minimum threshold and the last instrument goes dark and the transmitter loses the voltage needed to drive it. What remains will be silence and metal. The silence will expand at the speed of light in every direction and dissipate into the background noise of the universe within moments. The metal will drift. It will drift for longer than the Earth has existed. It will drift past the approach to AC Plasma 79 3D.8 and continue into the deeper galaxy, carrying its golden disk and its silent instruments and its corroded thermocouple junctions and the particular arrangement of wires and solder that 49 years ago constituted, briefly, one of the most sophisticated things humanity had ever made. In a billion years, the sun will have brightened enough to begin making Earth's surface uninhabitable. In 5 billion years, the red giant expansion will erase the surface entirely. In 100 billion years, the last stars in the universe will be cooling toward extinction, and the interstellar medium through which Voyager drifts will be thinning into a darkness more complete than anything that exists today. And Voyager will still be moving. Slower now, marginally, as the gravity of stars it passes tugs at it across the centuries. But moving, intact, silent, carrying a record of rain and music and a child's cry and a human kiss into a universe that will have forgotten, by then, that stars were ever warm enough to warm a world, that worlds were ever wet enough to fill with sound, that sound was ever shaped by anything as brief and strange and ardent as a human mouth. Voyager 1 is the longest goodbye our species has ever said, and the heartbreaking, clarifying, irreducible truth at the center of all of this, the truth that the pale blue dot photograph whispers and the golden record shouts and the dying power budget confirms, is that we said it anyway, knowing it would not be heard, knowing it would not be answered, knowing the universe would receive it with the same vast, patient, absolute indifference with which it receives everything. We said it anyway. That is what we are. That is all we are. And it turns out that is enough.